hosting this tutorial on SymPy. Yeah, so I'll leave the floor to them now.
Thank you, Jonathan. We'll start with a very simple, very few slides at the beginning. My name is Ondrej, this is Aaron. The last guy, Mateusz, has helped us with the tutorial, so he's among the authors as well, but he could not make it. First, we'll start with what SymPy is, and we'll show you some features just on the slides to get you a better idea what SymPy can do. Then we'll talk a little bit about history and about the current state, and also about what we plan to implement in SymPy in the future. And the tutorial will start with very basic things in SymPy, so you don't have to have any previous knowledge. And then we'll gradually build it up. And at the end, and so Aaron will take the basic tutorial. It will take about 2 hours, 2.5 hours. And then I will take over and I will show some applications of SymPy from real life, things that either I needed or my colleagues needed. And we used SymPy to achieve it. So let's start with the goal. The goal of SymPy is to provide a symbolic manipulation library in Python. Kind of a larger goal, that's what we have on our web pages, is that we want it to be in Python and open source. We want it to be self-contained so that it does not depend on any external libraries. But of course, optionally, you can use them from SymPy. And it should be easy to understand, it should be easy to extend, and easy for people to contribute to it. So let me just go very briefly over the features. So the core capabilities include all the usual things that you would expect from a symbolic manipulation library. So it can do basic arithmetics, simplification, expansion. It has all kinds of functions and special functions. It can do substitution. It can do pattern matching. It has a good support of polynomials. It can do like factorization and grab braces and so on. It has pretty good support for calculus. It can do limits, differentiation. It has a rich algorithm for integration. So you'll see during the tutorial that SymPy can do quite a lot of integrals. It has equation solvers. So it can solve polynomial equations, algebraic equations, differential equations, system of equations. Has some support for combinatorics, discrete math, matrices. So you can manipulate symbolic matrices. It has some support for geometry, plotting. Then SymPy has quite a few modules with applications. For example, in physics, it has a quantum mechanics module which can do quite a lot of quantum mechanics. It has some optics, and all kinds of applications. It has a module for statistics, and it also has a module for printing. So you can take the expression and print it in LaTeX and or generate code in C or Fortran. And you'll see most of these things in the tutorial. Let me just very briefly mention some history of SymPy. I started a project in about 2006, and most of the development have occurred from 2007 and later, when we took part of Google Summer of Code. In case you are not familiar with Google Summer of Code, Google is paying students to work on open source projects, and we have taken as a project part of it since 2007, so it's like 5 or 6 times already. And Aaron and most SymPy developers have joined through Google Summer of Code. Aaron is one of them. And since 2011, I stepped down from being the project leader and gave it to Aaron so that I can finish my PhD. And it was a lot of work, and Aaron actually has been doing a better job than I do. So I've been very, very happy about the choice. So currently, SymPy has about 250 contributors total. The code base is around 400,000 lines. And we are at the moment, I feel we are crossing the point from being a toy to being a tool. And what I mean by that, you'll see from the tutorial that usually when you want to get some things done, SymPy can usually do it. Maybe sometimes you need to help a little bit, but it's becoming a very useful tool. So let me just very briefly say a few things about what we work on at the moment. So we have 7 Google Summer of Code students this year, and so one of them is working on extending our symbolic integration and improving it. The other project is implementing faster polynomial algorithms. Another project is working on improving the differential equation solver in SymPy. Then we have a project in Lie algebras, vector calculus module, and also creating electromagnetism module with applications in electromagnetism, and finally a Diophantine equation solver. So these things will be implemented by the end of the summer, or should be. And then we have some more plans. One of the things we want is to implement better assumption support, so that you can assume that, for example, x plus y is positive, and then you can work with that, for example, in integration and other places. Make things faster, that's always our goal. And then we have some more things. If you are interested, you can click on the link below, and we have a lot of ideas that we either try to work on or will work on. Just to kind of give you an idea about how active the project is, we plotted a graph of about 6 or 7 open source projects, scientific projects like SymPy, IPython, numpy, matplotlib, and we plotted the number of commits on the y-axis and individual people on the x-axis. So, for example, and I plotted at the dashed line is an arbitrary threshold of 50 commits or more. So you can see how many people, for example, contributed 50 commits or more. So if you look, for example, at the blue line, that's SymPy, it's about 20 people. So in the last year, about 20 people contributed 50 commits or more. If you look at, let's say, scikit-learn, it's about 15 or 14. So it kind of gives you an idea how much about the commits. And this is, just kind of a rough measurement of a bus factor. Just for illustration, we also plotted all commits over in the whole history of the Git for all these projects. So you can see that SymPy is the blue line. You can see that there are a lot of people up to, for example, if you want to know how many people contributed 10 or more commits, it's right here. So it's about 150 people contributed 10 or more commits. So we try to be very welcoming to new contributors, and we'll be very happy to, if you would be interested to contribute to SymPy. We'll have a tutorial at the end, and we'll be very happy to guide you through it. Also, to be fair, we had a lot of Google Summer of Code students, and also coding. Coding is another thing that Google does. They do it that's for high school students, and I don't know if they are paid, if the students are paid.
It's actually a contest, so if whoever does the most stuff can win a prize, and I think the top prize is to actually go to Google's headquarters in California.
Right, and they are encouraged to contribute just very simple patches to a lot of projects, and so that might be one of the reasons why we have quite a large tail. We also wanted to thank all the authors of SymPy, that people that contributed at least one patch or more, and those are all the people.
There's 2 pages of this.
Yeah, first page, second page. So here at SciPy, there are, besides this tutorial, there are 3 talks. Matthew Rocklin will be talking on Thursday, and he uses, all these talks use SymPy in some way. Jason will talk on, you forgot to put the day for Jason. Do you know which day he talks?
Oh, I put it in there. I probably just didn't recompile, which means it's not in the...
Oh, here we go. So Jason will talk on Thursday as well, and finally David.
I put the day in the wrong spot.
David also talks on Thursday.
So David Lee is actually a high school student, and he was actually one of the Codin students that we mentioned. And he, you'll see later in our tutorial, there's this thing on our in our docs, this interactive shell that you can use. And so you can, this is arbitrary Python here, and you can get, while you're looking at our documentation, you can just click on one of the examples and it'll run it in here and you can play around with it. And he's also got this thing called SymPy Gamma, which is SymPy's version of Wolfram Alpha. So you can see it's pretty, I guess there's not a lot of randomness here. So I encourage you to go to all those talks. They'll all be interesting.
And finally, we'll have sprints, and one of our goals on Friday and Saturday, and one of our goals is to release SymPy2013, and also we'll be very happy if you be interested in development. You can stop by, and we'll be happy to get you through this. So let's begin, and Aaron will start with
just one note about the sprints.
Very simple.
If you do want to come to the sprints, we have a lot of tasks that are really good for people who've never contributed before. So, for example, we need to just write some release notes for the release. We've had a ton of pull requests merged, and that's pretty easy to do. And we also need to go through and close a bunch of pull requests that are open. So if you're interested in SymPy, want to learn more, encourage you to come to the sprint. Okay. And for those of you who didn't come in, how do I get back to the front? There is a website for this tutorial here. I don't know if you want to write this down. It's certik.github.io/SciPy2013 tutorial. And that'll have all the materials of what we're doing today. There's also some flash drives that should have gone around to everyone. If you need one, just find one. That also has all the materials. And there are some exercises, so you should get one of the flash drives. I am actually in the wrong directory with this notebook, so let me fix that. Okay, so I'm assuming everybody has SymPy installed already. Is that correct? If you don't, I'm told there's some kind of installation desk that you can go to that will help you. Just a quick question. How many people here have used SymPy before? Okay, good. How many people had heard of SymPy before they saw the tutorial? Okay, that's good. Well, we're going to start from scratch here. So I think this is just installation instructions here. We don't need to do this. So let me just give a brief intro to symbolic computation. This doesn't have that. So I'm going to be jumping back and forth between this notebook and our tutorial here. So let's say that we wanted to just compute the square root of something. So Python has, a math module. So you can do import math and math.square root of 9, and that'll give you an answer. But say we wanted to compute the square root of something else, like 8. So we get an answer here too, but this is a floating point number. And if you recall, the square root of 8 is actually equal to 2 times the square root of 2. And if you look at this number here, there's really no way that you can tell that because this is just a number. So the power of SymPy is that it does things symbolically. So if you use SymPy, I did not import SymPy. You get a symbolic answer. And so here, now if we move on to something more interesting, let's say that we take this, the more interesting thing is we can actually use symbols. So if we use this function symbols to create x symbols x and y, and then I do like 3 times x plus y, and here I get something symbolic, and we can So if I set this to a variable, so I can manipulate it, I can add stuff to it, I can square it. And one thing to note here is that when you square this, it doesn't expand it out by default. So SymPy, by default, it'll do really basic simplifications, like if you do x plus x, you'll get 2x. But if you do this thing squared, it won't expand it. And the idea is that you might want this to be factored, or you might want it to be expanded. So if you want either one, you have to explicitly tell it what you want. So if we put expand here. By the way, can everybody read what's on the screen? Because I can make this bigger. Okay, let's see if IPython notebook. Is that better? Okay, just let me know these things. So now if you can see we expand this now, and we get the expanded result. And so let's set that equal to a new variable. And then now if we wanted the factored version, we could factor it. So that's just kind of an idea of the sorts of things that you can do with symbolic computations. And here I've just listed, I guess this needs to be bigger as well. Yes?
Good question. For me to be able to do similar things, I have to install everything from SymPy.abc. Is that because I have a different version of SymPy? Or
From where?
from SymPy.abc? If not X, Y, and Z are not...
Oh, yeah, I'm going to get to that. So here is just a list of the sorts of things, and we already listed the features, so I'm just going to skip through this. Let me just go through, a lot of people ask us sometimes, like, what's so great about SymPy? Isn't there already Mathematica and Sage and Axiom and all these other computer algebra systems? So the first thing about SymPy is that it's completely free, open source. It's BSD licensed, so you can use it however you want, as opposed to things like Mathematica where you have to pay these expensive licenses. The next thing everybody here should be well aware of is that SymPy uses Python, so we should all know the advantages of that. So a lot of these computer algebra systems, in fact most of them, kind of invent their own language that you have to use when you want to use them. And it's kind of confusing. You have to learn this new language, and you can kind of tell this language was kind of designed by people who aren't really language designers. They're more mathematicians, so they're not really the best at designing a programming language that's easy to use. And so we just said, no, Python's already a really good language. Let's just use Python directly. And so if you want to use SymPy, the language is just Python. We didn't invent any new language with it. As far as Sage goes, people ask us a lot about Sage, which also uses Python. Sage has a different goal than SymPy. The goal of Sage is to actually be a full-featured computer algebra system, and the way that they're doing that is they're pulling together just about every open source system that there is into one package. So SymPy is actually included in Sage. SymPy, on the other hand, aims to be completely self-independent. It doesn't require any dependencies. And so, and finally, a very important thing about SymPy is that it can be used as a library, which is something that's really hard to do with something like Sage or even some of the proprietary systems like Maple and Mathematica. So if you have your own application and you want to ship something off to SymPy to do some symbolic applications, it's really easy. You just do import SymPy. Okay, let me skip the printing and go back to it. So as it was so duly noted, SymPy is built in Python, and so SymPy is constrained to the rules of Python. And one of the very important rules in Python is that you have to define variables before you can use them. So here, let me just start a new notebook. So here, let me say I import everything from SymPy. If I just do x, x is not defined. It's because x, the variable x in Python hasn't been defined. So if we want to make a symbol, we use the symbols function. So if I do like x, y, and z equals symbols x, y, z, now x is defined. But for example, the variable a is not defined. So this thing, if you want to use SymPy interactively, this thing can be kind of annoying sometimes, and there are some ways that we have that can make this easier. One of the ways that we have is this var function. So if you do var a, that'll create the variable a. And notice that I didn't have to assign the variable a here. Var just injects the name into the namespace. So var is kind of a hack. It does some injection using inspect module. So we recommend that you only use it interactively. Don't use it if you're writing a script or a program. Let's not use that. And so as far as another thing that often is confusing is that there are two things with a symbol. There's the Python variable, and then there's the symbol name. And the two things do not need to be the same at all. So, yeah, let's leave that. For example, I can type x equals symbols y. And then if I type x, I'll get the symbol y. This is because x here is the Python variable, and y is the name of the symbol. So what I recommend that you do is that you use the same name for Python variables and SymPy symbols. And the exception to that rule is if you want to, well, there are a few exceptions. One is if you want to use a really long name. So if you want to use like a Greek letter, you don't have to type out the letter each time. Another one is if you want to use something like that doesn't, something that's not valid Python syntax for a variable name. So you can put any character you want in the name of a symbol. But throughout this tutorial, we're going to be using the same variable names as symbol names. And so now, let's get on to another important point. So let's say I create some...
Can I ask a real quick question?
Yes.
So there's already a variable a. It's a squared. There's no relationship there, right?
Right. What I did here, okay, so let's be clear what I did here. This string here is just the name of the symbol. So I can put anything I want in here. I can put spaces, I can put letters, I can put something that looks like Python, and that'll just be the name. Well, okay, I can't put spaces if I use symbols. That'll just be the name of the symbol. So, you know, I can do something that looks like Python, but it's actually not. It's not really. This is just the name of the symbol.
Okay.
The reason that you might want to do this a up to is actually if you have printing enabled, it'll show the 2. So superscripted. Okay, so now let's say that I create some expression like x plus 1. Oh, x is still equal to y from over here. So let's go fix that. And then now say I set x equal to 4, and I print the expression. So what do you think that we're going to get here? So we are not going to get 5. We're going to get x plus 1. So when you set, you need to be really careful about the distinction between Python variables and SymPy symbols. If I create an expression and then I later go back and assign something to a Python variable, that doesn't change the expression at all. This expression is still x plus 1 here. So if we actually want to put 5 in there, we need to use the subs function like this. Well, first we need to put x back as a symbol. I guess I used 4, didn't I? So this is an important gotcha. So if just reassigning a variable in Python doesn't change what that variable was previously assigned to. And in fact, all SymPy expressions are immutable. So you can't change them in place. Whenever you do an operation on a SymPy expression, you will get a new expression back. So for example, here I did this substituted x equals 4, but if I print the expression again, it's still x plus 1. If I want to make this equal to 5 now, I need to do this. So that expr equals expr.subs x4. And then now it'll be 5.
So if it doesn't change x, you don't understand why the subsequent didn't work if you change x.
Oh, I put x back. Can you repeat the question? Oh, I have to. Oh, sorry. Yeah, I didn't realize that. So the question. Can you repeat it so I can hear what you said closer?
Where it says in 31.
In 31.
X equals 4.
Yeah, I have x equals x.
You need x subs. Oh, I see. Okay, never mind. Actually, no, I repeated those. So you had x equals 4. And
Yeah, no, I got rid of the x equals 4 because that was useless. I couldn't access the symbol x anymore.
I was confused why subs didn't work.
It didn't work when it was equal to 4 because this was saying subs 4 for, and it doesn't know what 4 is.
Yeah, we got confused between the x and the symbol again.
Yeah, no, I'm never going to reassign a symbol to a number again. That was just to show you. So okay, and so now let's go on to equals signs. I wish there were a way to do a Control L in the notebook. So let's say I have two expressions, like say x plus 1 squared. So let's call this expression 1. And let's call expression 2 x squared plus 2x plus 1. And I want to know if these two things are equal to each other. So let's say I just try the obvious thing. It says that they're not equal. Well, if you actually recall, these two things actually are equal to each other. So the reason that equals is saying that they're not equal is because they're not equal symbolically. So this here is x plus 1 squared, and this is a square, this is a power, and this here is the addition of some terms. So this double equals only checks if things are structurally equal. So if you want to know if two things are exactly equal, that's when you use the double equals. If you want to know if two things are mathematically equal, the best way to do it is to subtract one from the other and then try to simplify it. And if you subtract them and they simplify to 0, that means that they're equal. Question?
You mean they are, like when you say they're structurally equal, like two of the same shape equations would equal each other, or only if they're the same shape, or not the same shape, but the same structure and equal to each other?
What I mean structurally, I mean exactly equal. Like this printed expression basically needs to look exactly the same for them to be equal. So, I mean, you can have things that look the same. But with different symbols and stuff in there, but they're not equal. But here, if I put x plus 1 equals x plus 1, those are equal. Yes, those will be equal as well. So whenever you do addition or multiplication, it canonicalizes the order so that it doesn't matter what order you put it in. And in fact, it also prints in the same order too. Now, another thing that you might want to do is actually symbolically represent something as being equal. And for that, there's this EQ function. So you can, if you want to say x equals y, you just do EQ xy, and that'll create the symbolic equality. So let me assign that to something. And then now there's this, you can get at the left-hand side and right-hand side of that. Okay, let me see where we are with regard to these. Okay, does everybody have the exercise notebooks? Can everybody run those? This would be a good time to find that out. This thing that I've been holding. zip file. So run the notebook from the directory called tutorial exercises. And there's a notebook called gotchas, which is the section we're on right now. And if anybody needs help, just raise your hand and Ondrej will come around and help you. So our exercises today are going to vary from basic to more complicated. So if you can't solve all the exercises, don't feel bad about yourself. I put some in there that are for some of the more advanced people here today. But the ones in this first one should be straightforward. Okay, does everybody have the notebook open? Who doesn't have the notebook open yet? Okay, and can everyone execute this first cell without any tracebacks or anything?
I get a cannot no module name IPython.
Okay. Did you? All right. Can you go to the directory where this notebook is? Oh, you're using Git. Okay. If you're using Git, can I close it for you?
Yeah. Oh, yeah. I'm sorry. Hold on a second.
Your keyboard. Oh, it goes in Control C. It's okay.
Ah, cool.
If you're using Git, you need to type git submodule init and then git submodule update, because there's a submodule that we have in there. Okay. Let me just type it in this notebook. So. And you have to be at the base directory of the Git repo if you're going to do that. And if you used our flash drives, you don't have to worry about it because it's already in there. Question?
Well, yeah, it's having an error.
What does it say?
It's IPython _dot.
Yeah, that if you get, are you using? How did you get the exercises? Did you? Yeah, and it doesn't work. What does it say?
IPython _dot tester.
And it says that even if you got it from the thumb drive.
You have to run IPython in that directory.
Well, no, I have this stuff here that's supposed to add it to the path.
But you're grabbing from the paragraph.
Right, you need to CD into the tutorial exercises directory before you run the notebook. And it didn't work? Okay, well that means I should have tested it before.
Well, that is just
Okay, well that didn't work. This is what I get for putting things off until last night. Where are the flash drives? Can you raise your hand if you have flash drives? Let me just give you that. Does somebody want to volunteer to help me out with this? Maybe Ondrej can volunteer? I need help with, something didn't make it to this flash drive. I need to put it out to everybody.
I figured out, there's a folder on the flash drive that you should not be seeing into. Somebody unzips it on the flash drive.
Huh?
So you need to unzip the zip file, and then there's two directories you can CD into. There's one called SciPy_SymPy, and inside that directory is my Python project that has stuff in it.
Uh-huh.
There's another directory in the root of the flash drive.
Oh, so if you didn't copy the zip file, then you're in trouble? Is that what you're saying?
No, I'm saying there's two folders called tutorial exercises.
Uh-huh. Oh, there are? Well, there was the zip version and the unzip version on the flash drive. Which one did you use?
The unzipped version doesn't contain the stuff in it.
And the zip version did?
Yeah.
Oh, okay. Well, that's even...
There. If you copied everything off the thumb drive, just unzip the zip file.
So if you does anybody actually have it working who copied from the thumb drive?
I unzipped it.
Okay, so if you didn't copy the zip file, can you do that instead? And different thumb drives might be different too. So can you try to help people get this working? Sorry, there's always these issues. So how many people have this working right now? Okay, well if you don't have it working, I guess you can just watch or look at somebody next to you. Anyway, there's this this first cell you need to execute on each of these notebooks, and here are some exercises. And the way these exercises work is they're using this doc tester module, which isn't going to work here. So if I put like 1 here. So the way that this works is each of these functions has a doc test that explains what the output you should be getting. And then you fill in the function with the return statement with what you think the answer should be, and it'll tell you if you're right or not. And so we've so far covered the symbols and equality sections of the tutorial, so you can go ahead and do those 2 exercises. Are the flash drives making their way around to people who need them? If you have a flash drive and you're not using it, can you pass it forward to whoever? So if it's not working for you, can you raise your hand so we can see who needs? Is it just you?
I've got a no module named GMPY display hook.
Oh, that means your IPython's not working.
It seems to work fine. I don't know.
Well, what IPython are you using?
Development version.
Okay, we tested this on the release, so if you use Anaconda or EPD or whatever,
Maybe I'll try to go that route.
the zip drive, if you find one of the flash drives, they have Anaconda on them.
Okay.
Make sure I didn't forget anything here. Okay.